Okay, everyone. Welcome to today's seminar. In a moment, I'm going to introduce our guest speaker of the day. But I thought, first of all, I'd say a little bit about the MSc in Energy Systems, principally around where we are. We're currently in our 6th year of the course. We are flourishing in terms of application. We had over 255 applications so far this year from the first deadline. From that point of view, we're taking students from all over the world. So we have students from every single continent that's populated. We haven't yet any penguins apply, but we may at some point if it gets a bit warmer. So it gives me great pleasure to introduce one of our students from last year, Eleanor McIndo, who is going to be talking to us today about a piece of work that she did around the impact of climate change onto the Victorian transmission system. A piece of work that we are hoping to publish over the next couple of months. So watch this space also for the full academic output. So over to you.
Thank you. Everyone, so my name is Eleanor, and this presentation will be on my dissertation, which was on the future risks of climate change to the Victorian electricity system. And hopefully by the end of this presentation, you're as convinced as I am that Victoria's electricity system must prepare for climate change. That works.
Yeah, that one.
Usually works. Okay, we'll have to do that. Okay, so the agenda for today. So firstly, I will explain why does this matter? So the consequences of historic power outages caused by heat waves in Victoria. I'll then move on to the current state of climate resilience planning in Victoria, Australia, and how prepared they are. I'll then explain how elevated temperatures threaten system security, so that we're all on the same page about what occurs when you have high temperatures. And then getting to the meat of my research, which was on the heatwave risks to the electricity system under a 2-degree future climate scenario. Now, I chose to look at 2 degrees because that corresponds to the top limit of the Paris Climate Agreement. So looking at if we get to our kind of minimum threshold that we want, how at risk is the Victorian electricity system. So I'll explain the methodology that I used, the development of generalized event definitions, and the probabilistic assessment of transmission, generation, and whole system risks, comparing the current climate to a potential 2-degree future scenario. And then moving on to the conclusion and questions. Okay, so firstly, why does this matter? So Victoria and Australia, as you probably would guess, is a heatwave prone area, and this can have very large social, economic, and system impacts. So over the past few decades, Victoria's experienced a few very large, widespread outages, which has affected hundreds of thousands of customers across the state. So there's been large social impacts. Over 500,000 customers lost power on 2 separate occasions. There have been a couple over 10,000, 50,000. In some cases, reconnection took days to weeks, and this can have very severe impacts on communications, health services, and transport disruptions. So there's a high human cost associated with power outages. There's also a high economic cost, so power disruptions have contributed to upwards of 800 million in losses in some cases, as well as response costs of over 32 million in January 2019. So you have high economic costs as well. And then the system impacts. So across these 7 heatwave outages that I analysed, there were 12 separate load shedding incidents when power was cut at a transmission system level to a very large number of customers. There was also the separation of the Victoria and New South Wales systems, which is a very kind of interconnected area, so that's quite substantial. There was also separations of the Vic system with 2 other states, so Tasmania and South Australia. There's been large infrastructure damage, which again has high costs associated with repairing that, and breached reliability standards. Now, the current state of climate resilience planning in Victoria, Australia is weak. There are systematic challenges because although there are provisions in law to look at the risks of extreme temperature, those don't extend to future risks. And because of that, it's difficult for investors to justify investments in climate resilience measures or adaptation requirements to shareholders and regulators. A project done by ESCI, which was funded by the Australian government, has found that the AEMO, which are our system operators, long-term plans, because of this lack of regard of future scenarios, is likely to result in an overestimation in the reliability of the electricity system. Now, this all matters because the future climate is not being considered for infrastructure that is being built now with operational lifetimes of several decades. So our system that is being built now may not be up to a future climate, but at least it's not being considered in the plans. Now, this is important because there's an accelerating investment in net zero. There's $3 billion in the current investment pipeline over the next few years in renewables, grid expansion, batteries, and the 6 renewable energy zones. You've also got increasing system complexity. So there's a 95% renewables target, which will increase variable renewable generation on the grid. There's a rapid shutdown of baseload coal, which comes with it a loss of traditional system inertia mechanisms to keep the grid stable. And you've also got a large increase in demand that is projected. So you've got kind of this accelerating investment in net zero and an increase in system complexity, which isn't, and then you've got a lack of kind of future planning with how climate change is going to affect these different aspects. Now, so what happens to the system when you've got extreme temperatures? This will just be a high-level overview, so we're on the same page. So firstly, you've got increased demand from increased cooling loads. As you can see here, this is a graph of the mean summer daily peak temperature in orange that you can see for every single year compared to the heat wave peak demand for the 7 heat wave instances that I analysed. So you've got significantly high peak demand. You've also got that peak shifting later into the afternoon, evening because of solar, which has some effects on reliability of other generation. At the same time, you've got lower conductor transfer capacity because high temperatures cause greater conductor sag, which can increase the risk of flashover. It's a little diagram on the right there, and can cause physical equipment damage. Now, because passing current through a conductor causes it to heat up, which can lead to these risks, operators will reduce the power transfer capacity during heat waves to minimize such risks. So therefore, power lines are assigned a static or dynamic temperature rating, indicating the maximum allowable current for safe operation. Generation is also affected during heat waves. So here we've got some power curves for different generation technologies. So on the left, you've got wind. This is a power curve taken from data on wind generation in Australia, in Victoria, and around New South Wales. So this shows what happens to the power at different temperatures and wind speeds. And you can see there is a decrease as you get to high temperatures, going down from about 35 degrees at the top to 45 degrees at the bottom, where you see an approximate 65% reduction in energy. For solar generation, you have a pretty stable level of power output until you get to about 50 degrees, at which point it drops significantly. You also have temperature derating of gas turbines above certain temperatures. So here, the big point is kind of around 35 degrees. That's what manufacturers call their threshold of kind of safe operation. So beyond that point, you either have to reduce your capacity to ensure you've got safe operation, or you have difficulties with cooling limitations and the actual thermodynamic process, which means that you generate less electricity. Now, all of this comes together in heat waves to create increased system stress and tighter margins. So you've got your increased demand from customers, your lower transfer capacity to transmit the electricity to where it needs to go, and reduced generation efficiency to actually create energy that is needed to cool everyone down. Because of this, it's harder to balance supply and demand, and there's also heat waves that are quite difficult as well because they're spatially distributed demand, which increases the risk of cascading line failures because you have a high proportion of lines that could be highly loaded. Now, as a last resort, system operators can activate load shedding, which will cut power to large numbers of people at the same time. Power outages can also occur because of overloading and equipment failures on the distribution network, where you basically get equipment faults because there's such high demand, which can cause localized outages at the distribution level. Okay. So now moving on to the methodology. I used a methodology adapted from climate attribution studies to examine the change in likelihoods of extreme heat wave events under the current climate and a potential future 2-degree warming scenario. To do this, I first had to analyze the historic heatwave outages in Victoria to understand what the physical heatwave conditions, system dynamics, and event impacts were that led to large-scale power outages. So to understand really what goes on in the Victorian system itself. So I used a couple of different data sources for that, including AMO reports, market reports, climate reanalysis data, and outage data from 4 distribution network operators in the state. Once I had an idea of how heatwave-induced power outages occurred in the Victorian system, I was able to create my event definitions, which have physical, spatial, and temporal components, and must be identifiable in historic meteorological data and climate model outputs. So basically, it gives you a kind of signal that you can look for in historic meteorological data and climate model data, so you can compare the relative likelihoods within the 2 data sets. Now, the event definitions were defined in relation to system impacts. That's why I needed to analyze the historic outage conditions, so that you can connect the physical and spatial components and thresholds to the actual power system impacts. And these were generalized to represent a class of similar events. Moving on from that, I evaluated the HAD-AM4 model outputs to see if it represented the observational data generally well, and it did. So that's the model that I used. I then went on to the meat of the analysis, which was the estimation of the event likelihood and probability ratio. So to do that, I calculated the mean temperatures across the different spatial scopes of my event definitions for over 1,000 simulated periods. I then used the empirical cumulative distribution function to calculate my event likelihoods and probability ratios, and used a non-parametric bootstrap approach to determine the 5th and 95th percentile confidence intervals. Okay, so now I'm going to run through how I developed the event definitions. So firstly, the whole system. So the idea of this was to create a basically generalized event definition. So what are try to figure out what the physical components were that correlated with or were linked to your transmission, distribution, and distribution impacts all coming together to cause big, large-scale outages. So here is a visualization that I made of all of the 7 different outages and the effects at a transmission network level, generation level, and distribution level. So there's the map of Victoria there. You can see the lines indicate transmission, high-level transmission conductors. And the red icons are for issues on the transmission network, the green issues around generation, and blue issues around distribution. So some interesting things to note here is at the transmission level, there was, let's see if this pointer works. Kind of, okay, so up there on the left, you can see an interconnector to South Australia. There's also one down here to Tasmania, and then here and here we connect to the the New South Wales network. So along especially those interconnectors, you had a lot of either thermal constraints or equipment failures. Also can see in where, let's see, here, which is kind of the center of where a lot of different transmission lines connect together. You also had system faults. The fire icons show damage from bushfires as well, which is quite significant in a number of the outages. In terms of generation, you can see that the issues with generation were concentrated where the generation is. So Victoria has traditionally had a very centralized electricity system, which here you can see down the bottom. This is a Latrobe Valley, which has a lot of coal-fired power stations. So you can see instances of thermal limitations and equipment failures there that caused outages at the coal-fired power plants. And then to the west of Melbourne here, these are wind farms that in the last few years have sprung up, and they have also had issues during some heatwave events. The distribution level, because that was seen statewide, it's here in this kind of box here. You can see instances are reported. There are statewide issues, both at transmission, generation, and distribution network. There was a lot of instances of overloading, so high demand causing overload, as you'd expect. Going into a little more depth, the distribution level, this is a snapshot of some of the data that I collected from the DNOs. So the reason I want to do this is to kind of understand at a more granular level what were the actual causes of the power outages. So here you can see I've filtered it into the 4 kind of big umbrella causes. You've got overloading, load shedding, asset failure, and weather. On the far left, you've got the number of customers affected by outage cause for each of the outages. In the middle, you've got total customer minutes lost by outage cause. Customer minutes lost is the number of customers times by the length of the outage. So that's a good indicator of outage severity. And then at the end, you've got frequency of outages by 6-hour period and cause. So what the analysis of the DNO's data showed us was that overloading and extreme weather were primary drivers of outages and outage severity. Load shedding was also quite significant in terms of the number of customers that it affected, but in terms of outage severity, it was the third driver because your overloading and weather caused outages for longer durations. Then there's also the presence of concurrent extreme weather during heat waves also greatly exacerbates the severity of outages. So that's your storms and your bushfires. And then outages on the far right, the frequency of outages, you can see that outages occurred across the day, but mostly during that afternoon period, as you'd expect. There's some more data that's not up here that shows that outage durations were on average, between 3 to 6 hours long, depending on the network. I then looked at so that was the causes of outages, which kind of validates what I found out through the literature review. So those are kind of the main causes of outages in Victoria. Now, looking at the physical conditions that led to outages, we've got the temporal variation that I was looking at and the spatial variation. So to do this, I used ERA5 climate reanalysis data, which on the far left here, easy to see. So this is just a snapshot of one of the outages in 2014. So on the far left, you've got the temperature variation for each 6-hour period across the outage and the 3 days either side. And in pink, I've highlighted when outages were reported in newspapers, AEMA reports, and DNO data. And this showed us, there were patterns across all of the different outages that showed that during large scale outages, you got a high state maximum and minimum temperature. So that's the top in the red and the bottom in the green. Your mean state temperature was also significantly closer to your maximum state temperature compared to the days on either side. And it validated that outages correlated with, or it supported the idea that outages correlated with high temperatures rather than accumulated heat effect. So looking at when temperatures were high, we could link that to outage severity rather than looking at the, say, the 3rd day of the outage, the 4th day of the outage. The 4th day of the heat wave. The spatial variation across the heat waves, they all looked like this, a big mass of red with some yellows. The red corresponds to temperatures above 40 degrees. The yellow here is still above 30 or 35 degrees, so it's very hot across the entire state. There was, across the different heat waves, there was a low standard deviation of your gridded 6-hour mean temperatures. This is the grids taken from ERA5 climate reanalysis data. And very high temperatures were seen across the state. In non-heat wave days, the pattern here looks very different. You have kind of the whole color spectrum. So some areas might be very red, some areas green, some areas blue. In these big statewide heat waves, you had very high temperatures across the whole state. Now I looked at the comparing the spatial distribution of temperatures with the outage severity. So here you can see the location of outages from the DNO data. The dots here are just the central point in areas, so it should be a bit wider than what you see. But this basically showed that there was a correlation between outage location and ambient temperature. Now, this all seems kind of intuitive, but it could have been that we saw more outage severity in very high population areas like Melbourne, even though there was high temperatures all across the state. So this kind of this validated that you get outages, and in terms of both load shedding and overloading at the local distribution network whenever there's an instant high ambient temperature. So using the analysis from the last 2 slides, I was able to come up with my event definition, which is using mean 6-hourly ambient temperatures averaged over the Victorian state boundaries as the different components for my whole system event. Now, this needs to be linked with an event severity threshold. And to do that, I calculated percentage failure rates, which indicate the proportion of 6-hour periods between December 2008 and March 2024, which is the time period of the outages that I was looking at, when exceeding a particular temperature threshold or mean state temperature threshold resulted in significant statewide load shedding or power outages. And here are the results. So at 39 degrees, there was a 100% failure rate. There was only 3 instances when that ever happened, and they all caused massive outages. 38 degrees was corresponded to 70, and you can see the others here. Now, it's important to note that this percentage failure rate should be seen as an indication of or a representation of the current system's resilience level. Now, because there's not a huge data sample, it's not necessarily like every single time it will happen. It should be more shown as this is what has happened in the past. So let's compare it now with a potential future climate. Okay. Now, the event definitions for the transmission network and generation were much easier to define. So for transmission, the spatial scope was the transmission network. So here you can see a shapefile of the Victorian transmission network, and then this is the gridded data from the HAD model that I took for that spatial scale. Same for for generation. I took the 6 renewable energy zones that the government is planning on in pushing renewable development in, and this is the corresponding zones in the HAD model. The temperature was similar, so using the temporal scale was similar, so using the 6 hourly mean temperature, and the event severity thresholds were taken from either literature or AEMO system documents. So for the transmission network, these are the static and dynamic ratings that are used by the system operator for both planning transmission lines and the operation. So these should be seen as the kind of the maximum temperature that they plan for. So if we have a 40-degree day, the system should be able to cope with that. Is essentially what this means. For generation, I took the temperature thresholds from the power curves that were shown earlier. So for wind, a 20% reduction was seen at 40 degrees and about 65 at 45. And for solar, again, 20% at about 40 degrees and a large drop off at 50. For battery systems and gas power plants, 35 degrees was selected, as that's currently commonly seen as kind of your maximum safe operating temperature. Okay. So here are the results of the whole system event definition, the whole system analysis. So on the x-axis, you can see the mean 6-hour state temperature, and on the y-axis is the chance of the event occurring in a given summer. So this is a 1 in 1,000, 1 in 100, and so on. Orange shows the 2-degree modeled climate, and blue shows the current climate. And here is our threshold, which corresponds to a 100% failure rate or historic failure rate, assuming the current level of system resilience. So you can see there's a significant increase in event likelihood of a 100% failure rate event between the current climate here, which is about a 28% likelihood every summer, to the future climate, which has a 206% likelihood every summer. So it's moving from a once every 5-ish years to twice a year. Now that's very significant when we think about the human costs, the economic costs, and the system costs of such an event happening. Now, on the left, it shows the probability ratio of exceeding temperature thresholds in the future climate, and the right shows the probability ratios compared with for each event likelihood. So just to go through this quickly, this one here shows basically for each temperature, what is the increased likelihood of such an event. So remember, this is your statewide 6-hour mean temperature under the future climate. So here is our event 100% failure rate, and that is 7.48 times more likely under a future 2-degree climate. Now this one here is showing the event chance with probability ratio. This should be very interesting for people in the insurance industry, for example, because a lot of this infrastructure is built according to a 1 in 10 event. So or a 1 in 15 event. So we have to build this system to be able to withstand such an event. So currently for transmission lines, in a international standard that's used often is a 1 in 15 year event, which is somewhere around here, which again you can see is between around about 6 to 8 times more likely in a future scenario. So moving on to the transmission risks. So again, you can see a significant increase in event likelihood for your 40-degree static or dynamic temperature rating. So remember that corresponds to the temperature that these transmission lines are built to, at the maximum temperature they're kind of built to operate at safely and reliably before having to take other measures to protect the system. So that will increase from about an 18% chance under the current climate to a 165% chance. So again, more than once a summer. And the probability ratio is 9.45. So again, similar things you've shown, it's much more likely that such an event would occur under the future climate. The generation risks are also very interesting. So the top line here in the orange is your 45-degree threshold. So that corresponds to a 95% reduction in wind, sorry, a 65% reduction in wind generation. Now this is not simulated under the current climate and becomes a possibility in a 2-degree scenario. About a 14% chance every summer. The line below is your 40-degree threshold, so that corresponds with a 20% reduction in wind and solar capacity. And again, you can see an increased exceedance likelihood of that threshold from about 31% chance under the current climate to a 239% chance. So a very large chance. In future climate. Now these are the same analyses done for gas power plants and battery, and your significant 50-degree drop in solar capacity. So for gas and batteries, it's quite difficult because their threshold really depends on a lot of different operating factors, but using that 39-degree threshold, the likelihood increases from 762% to 1,686% in your 2-degree scenario, corresponding to a 2.21 probability ratio. And your solar PV production, which if you remember from that graph before, was a very sharp drop. It's not simulated in the current environment and is about a 0.6% chance in a 2-degree future scenario. Now, what this all means is that we can see that heat waves are expected to intensify under future climate change, and this poses a risk to the security of the Victorian electricity system. The lack of regulations and industry standards to adequately assess and mitigate these risks could cause a problem for Victoria moving forwards if it's not addressed, seeing as there's a lot of infrastructure that is being built now that is meant to last for decades. The probabilistic approach shows significantly increased likelihoods of exceeding critical whole system, transmission and generation temperature thresholds under a 2-degree warming scenario. And the results demonstrate the need to incorporate climate resilience into energy security planning to ensure system security at least cost.
Thank you very much.